Hello again. This should be the video you're watching on Wednesday. This one is about switches as well as batteries within electric circuits. If you're looking at the presentation separately, we're starting off on slide 14 here. So to talk about switches in a circuit, they are kind of the connectors and the breakers of circuits. You can see on the left here, the schematic representation of a switch is just, well, the wires are straight lines, but if there is kind of a picture of a wire being lifted up, sort of, that is an example of a switch. You can think of it like a railroad track that can reorient with levers. The way we complete a circuit in most cases is by closing a switch. You can see in the picture on the right, this is a full schematic of a circuit. We'll talk about that in a little more detail later. But you can see there is, this is the schematic representation of a battery. Here's a light bulb, and then here's a switch. The battery provides the voltage for the circuit, that is, energy per coulomb that passes through. Current would flow, that is the charge every moment that flows through these wires, flows through some object that we're powering, maybe a light bulb, back to the battery, and the electrons gain their voltage back and make the trip again. But that won't happen if there's an open switch, as we see here. There will be no current flow in this circuit, and that's because with the open switch, the electrons are not able to jump from the end of the switch into the circuit again. Air is too good of an insulator to allow for that. In fact, one of the more intense times that air is ionized and allows for current to flow is, well, minor example would be when you get a shock on a doorknob, for example. But the most extreme case of this happening is a lightning strike. With a lightning strike, the potential difference, that is the voltage between the clouds and the ground, is so high that even the air, which normally is an excellent insulator against charge flow, becomes ionized, and the current from the cloud to the ground travels through the air, and that again is a lightning strike. But our circuits are not generating voltages nearly high enough that clouds and the earth do with lightning. And so again, the charge will never jump over a switch, and therefore when a switch is open like this, that is not connected, current will not flow, and therefore this light bulb will not turn on. So there are a couple of terms to describe switches in these two positions they can be in. When the switch is not connected, that is called open. And then when the switch is connected, that's called closed. When switches are closed, the circuit is active. You can look at a very simple example, probably on the wall of your room right now. I've got one here as well, a light switch. There's a lamp above my head. If I flip this switch off, I've opened the circuit, and now the electrons are not flowing, the light is not on. If I flip the light switch back in the on position, that is also called the closed position. I've closed the circuit and allowed the electrons to flow. So it's a little confusing with the open being off and closed being on. You think of open being, flowing. Like you open a door, you're able to go through it, but kind of the opposite in the case of circuits and switches. So one of the more interesting cases of switches in a circuit, especially in our residential homes, is the circuit breaker panel. You've all got one of these in your home. Maybe it's in your basement or garage. These are safety features. Of course, our homes are powered. Their current comes from the electrical wires, from the, starting off in the power. The power companies control the power stations, and that electricity generated goes through the telephone poles, step down at transformer stations, and eventually they're pumped into our houses. But they go through the circuit breaker panel first. So what these circuit breakers do, if you're not aware, is each of these individual switches controls one circuit in your house. Your house is not just one big circuit. It's couple of dozen circuits. If any one of these circuits detects too much current running through, it'll automatically trip or switch itself off. And this little lever will flip to the other side, breaking the circuit by opening its switch. You might see some differences if you check out your own circuit breaker panel, which you're going to in the assignment you're going to take a look at the end of this video. They have different numbers on different switches. Some of the switches are linked together. These numbers represent the maximum current that circuit will allow before tripping itself and therefore, breaking the circuit. That's why they're called circuit breakers. You're going to take a look at these circuit breakers a little closer with the investigation I left for you. So I'll leave it here for now, and you can take a look yourself. All right, I also want to talk to you about the battery today. The battery is the main source of, power for the circuit, although I should be careful with that word. Power is its own measurement that the battery does not directly provide. What a battery does is it supplies a potential difference to allow electrons to flow. Again, that potential difference is another way of saying voltage. All your batteries have two terminals, a positive and a negative terminal. There is a potential difference between these 2 points. Even right now, this battery isn't hooked up to anything, but there is an electric potential difference or a voltage between one terminal and the other. Batteries are actually more complex versions of a simple potential difference, which is called a cell. If we have several cells lined up in a row, which is what's going on inside of a battery, that's what a battery is called. You kind of get the idea of where the name of one of our more popular battery manufacturers comes from. So all of our standard batteries are several cells lined up to make a battery. But like I said before, the battery supplies voltage to a circuit. Now, the battery was invented by an Italian physicist named Alessandro Volta, which is why we name the unit of voltage the battery, the volt rather. This is back in the late 1700s. Still recent as far as most of classical physics goes, though. So like I said before, batteries are providing a potential difference or a voltage between their terminals, and they accomplish that by a chemical reaction. There's a video coming up very soon that you'll watch to get a little more detail about that. But you might remember learning about this in chemistry, in fact. But I do have a question I'd like you to think about. I showed you a AA battery a minute ago, and here's a picture of one as well. You can even see the 1.5 volts once my bar goes away. These batteries, AA's, AAA's, C, D batteries, the common ones we use, they're all 1.5 volts. If you don't believe me, I've got a picture on the screen, but you can take a look at, maybe open up your calculator, take a look at the AAA batteries inside. It's going to say 1.5 volts on it. So do C and D batteries. So the voltage is not different among these batteries. So what actually is different about them? And I'm not really talking about their size. Obviously, that's also a difference. But in terms of, electrical measurements, if not the voltage, what could be different about these batteries? Think about that. I've got a question about it on the exit ticket. So here is a video about a little more detail about how batteries work. I'd like you to watch it. It's only 4 minutes long. Hopefully you find that interesting. Again, it might remind you of some things you may have learned in chemistry class. But until then, until tomorrow, you can take a look at this video, take a look at exit ticket number 3, as well as the circuit breaker assignment. Hopefully you learn a little bit about the circuits in your house with that investigation. I'll see you tomorrow. We'll talk about resistance. Bye-bye.